Welcome back to our session on statistical significance and undersampling. In this last short video of the session, I want to come back to the second key question that we identified regarding how many samples do we need? The answer to that really depends on the question you want to answer. As I keep emphasizing during this course, information theory is all about questions and answers. And it's important that we're specific in what question we want to answer here when we ask how many samples do we need. One question we might want to answer is how many samples do we need to detect a statistically significant relationship between our variables? And there isn't really a good answer to that question because it really depends on the strength of the relationship. If the relationship between our variables x and y are quite strong, we won't need many samples at all to detect a statistically significant relationship there. But if it's a very weak relationship, we may need a whole lot of samples, and it's difficult to know where to draw that line. Typically, though, we're limited by the amount of data that we have, and so we can simply answer the question by saying whether or not there is a statistically significant relationship that we can reveal from the data that we are given. We can then ask how many samples do we need to avoid undersampling in general, thinking more about getting an accurate estimate rather than specifically a statistically significant estimate, statistically significant measurement of a relationship or not. When we're thinking about how many samples we need to avoid undersampling, that really depends heavily on the estimator. Let's think first about our plug-in Discrete Estimator. There are some fairly well-known heuristics for that. I'm going to show you one here from Lungarella and Company, who suggested to use around 3 times as many samples as there are possible state configurations in the data. And Lungarella and Company suggest having about 3 times as many samples. I'd go a lot higher than that, probably at least 10 times or more. What I mean by that is shown on the next line here. Considering a mutual information between x and y, we have the total number of state configurations here is the state size of variable x, or the alphabet size of variable x, multiplied by the alphabet size of variable y. We can see very easily that for binary variables there are 2 by 2 state configurations, which I've drawn out in this 2 by 2 matrix here. We can understand very easily then that the number of state configurations increases as each of these variables have more discrete levels or a larger alphabet size. So here that would simply mean we would be starting to have more more columns here for more discrete symbols for x, and more rows here for more discrete symbols for y. Similarly, if the variables become multivariate, this is basically doing the same thing as far as discrete data is concerned. But if we think about continuous value data, that means something specific there. So that in both of these cases, that is going to mean more potential, a larger state space, if you will. Also, as may or may not be obvious, we can use the same criteria for designing an analysis. That is, instead of asking how many samples we need for a given dimensionality or number of joint variables, we can ask what is the dimensionality of analysis that will be supported by the given number of samples that we have. So, if we are given n samples of a continuous value data set, we can then compute how many discrete bins we would be able to discretize that data into, producing a state space for our analysis that would not be undersampled. Similarly, we could compute how many joint variables of a given dimensionality that we could include in, say, a joint mutual information calculation from a given number of samples before we were to start undersampling. Indeed, it's probably more typical that you'll end up using this criteria in designing the parameters of your analysis rather than adjusting the number of samples. Coming back to the criteria itself, in all of the above, we've assumed that all possible state configurations are equally likely to be sampled. This is an easy approach to take. It's easy to heuristically calculate the number of samples required or to design the number of joint variables we can analyze in this way. But it's not necessarily always the case that all possible state configurations are equally likely, or indeed even occur at all. For large multivariate spaces, often only a subset of that configuration space may be explored, and this is called the typical set of state configurations. That is where the sample entropy is said to be close to the true entropy of the joint state. And we can think about the typical set as the set of state configurations that are likely to be encountered frequently enough in order to contribute to the entropy here. Now that is the set that needs to be sampled well enough, with the number of samples for that set equal to three times the size of that typical set, or in general, let's say some multiplier n, where I suggest we take n being probably more like 10 times or more. Now, you may not often come across need to invoke this idea of a typical set. In certain cases, you definitely will. There are very good expressions for the size of the typical set when we're dealing with entropy rates or block entropies in time series data. I won't go into that right now. You can see more details on that when we hit the information storage session, or by looking at the specific sections in the references below. So far we've really just been talking about the plugin or discrete estimator. You can adapt what we've spoken about here for the box kernel estimator heuristically. Basically there we think about how our kernel width kind of effectively splits up each dimension of the data into almost like carving it up into bins. When we can think about the typical spread of the data by assuming that the data normally spans about 6 standard deviations. I won't go into the mathematics of how to do that, how to make an approximation for the box kernel here. You can read the references below if you're interested in that. In terms of the KSG estimator, it basically adapts the bin width to avoid undersampling in general. I say in general because that's as long as you use at least k equals 4 nearest neighbors. Undersampling can occur sometimes when you go smaller than that, so I would not do that. Otherwise, you don't have to worry too much there about undersampling. It's going to adjust itself to the number of samples that you have. Now, that may miss subtleties in the relationship between your variables that occur on a smaller spatial scale than you are able to analyze for the given amount of data that you have. So that's something to be aware of. So let's close off this session regarding statistical significance and undersampling. What we've done here is to review the estimation of information as a statistic, and we've looked at how to test for that statistic both empirically from a given sampling of data and analytically where possible. And we looked at that specifically for the linear Gaussian and the discrete or plugin estimators, and we're hoping to have other analytic expressions for other estimators in the future. So I've shown you how to apply statistical significance testing of mutual information, conditional mutual information, and other measures based on those using JIDT. So you should be ready to go and do that now and answer the question that keeps coming up about, when we get a small value, is it statistically different to 0 or not? You can do that now. Coming up in the course, we're going to be turning our attention to looking at how to apply information theory to study complex systems, and in particular to look at information processing. And that's coming up in the next few sessions.